Hello, my name is Mohit Dalwadi, and I'm going to talk to you about levitating cylinders on thin viscous fluids. This is joint work with the colleagues listed here. In this work, Tom Mullin performs levitation experiments. He sets up a thin layer of upwards moving silicon oil on a conveyor belt. This is done by passing a conveyor belt through a bath of silicon oil and using a scraper at the base of the upwards moving belt to control the thickness of the film. He then puts a cylinder on the belt and tries to find a belt speed which allows the cylinder to remain stationary in the laboratory frame, essentially levitating the cylinder in place. Here are some videos of the experiment from the front and from the side. You can see that while the cylinder's centre of mass stays in place, the cylinder is rotating about itself at a constant angular velocity. One additional thing to note is that this rotational velocity is less than the belt velocity, typically at a factor of between 0.3 to 0.6, so there is some slippage here. We want to model, understand and quantify this interesting physical phenomenon. However, it's not straightforward, as this is a problem of fluid structure interaction. The flow of the silicon oil will affect the motion of the cylinder, and vice versa. Moreover, for a given cylinder, we don't know a priori the belt speed, u, that will balance the cylinder, nor the resulting rotation rate of the cylinder, omega. While the fluid layer is thin, it is helpful to present the full problem at the outset. From the geometry of the setup, we will consider a 2D problem. Since the shear stress induced by the belt causes the cylinder to rotate, some of the silicon oil that travels under the cylinder will loop around and cover the top of the cylinder, so we don't have a silicon cylinder air triple point in the model, and this is consistent with experimental observations. So, inside the fluid, we have incompressible Stokes flow in 2D. At the liquid-solid interfaces, we have no flux and no slip, and at the liquid-air interface, we have normal stress balancing surface tension, no tangential stress, and a kinematic boundary condition. We also need to know how the cylinder moves. So we have two linear force balances for the centre of mass, and one torque balance for the rotation. Given that we have a thin film, it will probably come as no surprise that we exploit this extreme geometry to understand the problem using matched asymptotic expansions. To give you the punchline of this analysis, the asymptotic structure of the problem looks like this, where epsilon is the ratio of the upstream film height to the cylinder radius. Some of these regions will be more important than others. One of the most important regions is the nip region between the cylinder and the belt. Due to the circular geometry, this has a standard square root of epsilon scaling in the x direction. Essentially, in this region you have lubrication flow leading to Reynolds' equation for the pressure, as you might expect. However, the fact that we don't yet know where this region terminates means the problem is a little more involved than standard lubrication problems. At this stage, it is helpful to count the number of unknowns in the problem to understand what is required of us. So we have two unknowns from having a second order ODE, two unknown velocities, the belt speed and the rotation rate. We don't know where this region starts and finishes, so this adds two more unknowns. And we don't know where the cylinder sits above the belt. The nip height is unknown. Altogether, this is 7 unknowns. So we really want 7 equations out of our analysis. Well, we have 3 equations from the force and torque balances. Then we probably have 2 more from imposing ambient pressure at either end. But this still leaves us requiring 2 additional constraints. How should we resolve this? The answer is through the systematic use of matched asymptotic expansions. If we want to use lubrication theory in the nip region, which is formally derived through an asymptotic analysis, we should expect to close the problem through matched asymptotic expansions. So let's go back to the full asymptotic structure of the problem. The issue causing us hassle is that the nip region terminates at finite points that we don't know a priori. Our problem in the nip region is essentially a free boundary problem. To understand how to close the problem, we must investigate the small coalescence and separation regions at either end of the nip region. In the downstream separation region, the leading order problem is basically separating Stokes flow in a channel where the top and bottom plates have different velocities, with surface tension being important on the interface. Although there are quite a few unknowns in this inner problem, the way you can characterise the solution space is by solving the problem for given plate velocities, then calculating the far-field separation heights. If you sweep through the 2D space of plate velocities, then you obtain a relationship between the velocities and the scaled flux through the system, Q+, in a kind of eigenvalue problem. This is where Radu rides in to the rescue. He was able to solve this problem via DNS by modelling the full coupled gas and liquid dynamics in this inner region and appropriately relaxing to the steady solution. Although he could give a separate talk on the details of this, in the interest of time I'm going to skip over the details and just show you an example of the results for one particular set of parameters. So we can have a look at these DNS results and what they tell us about the relationship between the velocities and the scaled flux. As you might expect, a higher cylinder rotation rate leads to a thicker film on the cylinder, but a slightly thinner film on the belt. Surprisingly, if we combine these results to calculate the ratio of the film heights, we see that these results all collapse onto a single curve, characterised by the cylinder rotation rate. Now, I can understand why this happens for small capillary numbers. You can solve this problem asymptotically in that limit, but not for moderate and large capillary numbers. I'd love to hear from you if you have an explanation of this. In any case, it is helpful now to summarise what we have learned from this inner analysis. Firstly, the pressure in this region is asymptotically smaller than the pressure within the nip region, and so we are able to impose ambient pressure at the ends of the nip region. Secondly, this numerical solution to the inner problem provides a relationship between the actual flux through the system and the position of the free boundary. This yields 2 conditions for each inner region, so 4 additional conditions in total. These 4 conditions are enough to fully close the problem. Essentially, we end up with 7 nonlinear algebraic equations for 7 unknowns, and we can solve this in a fraction of a second for any particular experimental setup. The real test is whether our theory matches the experiment. From our theory, we can construct a predicted experimental curve in terms of various parameter groupings. Here, you can basically think of the x-axis as an observed cylinder rotation rate, and the y-axis as an observed belt speed for levitation, both appropriately scaled. Tom has carried out experiments for a wide range of different film thicknesses and cylinder radii. The colours represent different film thicknesses, and you can see that they all appear to fall on our predicted curve pretty well. There is a slight discrepancy for films of thickness 0.2 mm, represented by the circles, but as belt roughness effects would be more important for thinner films, we think this might explain the discrepancy. So one interesting corollary of these results is that we predict a minimum velocity for levitation to ever occur, and that as we approach this, the cylinder rotation rate should tend to 0, sort of a passive slippage of the cylinder. However, it turns out that in this limit, the extent of the nip region tends to infinity, and so this limit corresponds to a cylinder being completely submerged in silicon oil, potentially leading to a breakdown in the extreme parameter ratio on which our analysis relies. In fact, what actually happens in this limit is that the small fluid gravity in the problem becomes more important, and so this submerged limit is never actually reached. This is quite interesting, because it might explain the slight breaking of symmetry that can sometimes be seen in the experiments. All of the results I have shown you so far suggest that the nip region is symmetric around the cylinder. However, including gravity can actually break this symmetry. Very briefly, including this small effect of fluid gravity seems to have a significant effect in the limit of light cylinders. These are the results I showed you previously, where we neglect the effect of gravity on the fluid. But if I add in a small fluid gravity, you end up with a bifurcation in the solution structure of the equations we derived, which correspond to asymmetric solutions. Unfortunately, the pandemic has meant that Tom hasn't been able to get back into the lab to test these predictions, but we suspect that these bifurcations correspond to the onset of long tongues forming below the cylinder. This is not something that occurs for the data presented here, but is something that Tom has observed if the cylinders become too small, as seen in this figure on the lower left. I think this is a nice place to end. Thank you very much for watching this talk.